All right, guys, we're going to go ahead and get started. I apologize for the late start today. I got kind of tied up this morning. I think what I'm going to do is from now on, we're going to start the class at 9 a.m. instead of 8:30. Give us a little bit more breathing time in the morning. So I'll post that. I'll send out an announcement. But starting next class, which is Wednesday, we'll start the session at 9 a.m. and then we'll go through however much time it takes us to get through the lecture. One announcement is you want to make sure. I met a couple people on Saturday. A couple students came up and got their kits, their analog kits for lab. There were several people that came up, and it was good seeing you. If you did not do that, we're going to be up there again. Well, someone will be there again from 3 to 6 today, and also tomorrow. I think 3 to 6 tomorrow, but you have to check. I'm not sure. Look at that schedule. You want to make sure between today and tomorrow you get up to the school and get that packet. If you wait till after tomorrow, I'm not sure how you'll get it because I don't know if they have any other times scheduled. So if you have any issues or problems, let me know, and maybe I can grab one and bring it to my house or something, and we can figure something out. But between today and tomorrow, you want to go ahead and get that done. Also, quiz 2 is posted, and I believe it's due tonight. You want to check that. Most of the stuff on quiz 2 you should be able to do. After today's lecture, you should be able to do everything on quiz 2. Quiz 1 was supposed to be an introduction. You guys log on, show your camera, introduce yourself to the class, and we tried that last time, and it crashed the system. So I got to figure out how we're going to do that. I'll figure something out for quiz 1. I'm not really sure right now, but we'll worry about that a little bit later. Anybody have any questions of me before we start?
Yeah, you did. You were supposed to email me yesterday concerning a model number for a recommended kit. Do you have one of those?
I do. Actually, Dr. Whaley just sent me the recommended digital multimeter model and the recommended kit. So tell you what, after class, send me another text with your email in it, and as soon as we get done here, I'll go up and I'll send that out. Probably just send it out to the whole class. Speaking of that, guys, so you do want to go ahead. The first lab you won't need any equipment for. You can do that. It's just kind of you watch a video and you'll describe some things. There'll be one on multisim. But you will need that packet, you will need the meter, and you will need the trainer. So I'll go ahead and I'll send out a link to Dr. Whaley has a website. I believe it's called DigiKey. I'm not sure, but he recommended a certain model digital multimeter and a link to where you can get the trainer from to buy the trainer. What I would do is just shop around on the trainer. If you get financial aid, you can get it from the bookstore. I think it costs like $100 more than we'll pay for a typical price online. But if you're using financial aid, then you should be able to get it from the bookstore like right away. If not, look at the link that I'll send you, but also shop around. Just make sure you match up the model number. The other thing is there's 2 types of kits. One is assembled, the other is non-assembled. I would highly recommend you get the assembled kit, not the one that you got to assemble, because if you run into a problem, you're still going to be without a kit. So I know I had 1 or 2 people that wanted to get one, and one person wanted to get one and put it together. The problem is if you don't have it together by the time we need to use it, or if something's wrong with it, or if you just don't put it together right, then we got an issue. So make sure you get the one that says assembled. I don't know who that was. It just asked about that, but if you don't get that from me like by the end of this, right after the end of the lecture, just send me a text and I'll post that to Blackboard. Any other questions before we start? Okay, well, one last thing. I know we're doing this remote video thing, and I don't know if I can even do this or not because they have so many layers you have to go through, but I like to do a couple face-to-face sessions in the lab. So I don't know if I can do it. I'm looking into it. I was told that some classes are meeting face-to-face for certain labs. So if I can arrange that, I'm going to kind of poll you guys to see who would be interested in having a couple face-to-face sessions. in the lab. But we'll see. I'll find out more information this week, and I'll let you know about that as we go. I'm going to go ahead and get started now. We're a little behind. That's okay. We're still in Module 1. And in Module 1, we were talking about understanding voltage, current, and resistance. Now, I've already posted the information for Module 2. I don't know if we'll get to that today or not, but if we don't, it's okay. But you want to go ahead and print that out, 3-hole punch it, and put it in your class notebook. You can kind of read ahead and kind of look at that stuff as we approach that material. But in the last lecture, we talked about this concept of charge. Now, remember, we're trying to understand the nature of these quantities that I have written on the board. These are the ones that we can measure. These are the ones that most people are familiar with. And there's other quantities that we can't measure directly, but we can get to them. We can calculate. We can derive them from these fundamental electrical quantities. And so in the last class, we talked about this concept of charge. And we talked about the fact that I can use that term charge as a noun. I can use that term charge as a verb. As a noun, it's something an object possesses. As a matter of fact, the two objects, the two things that we talk about that possess charge, one is called the proton, the other is called the electron. And we know that the proton possesses positive charge and the electron possesses negative charge. We also learned about the law of charge. The law of charge says like charges repel and unlike charges attract. Like charges repel and unlike charges attract. So we can use the term charge as a noun, but most of the time people use that term charge, they're using it as a verb, something you can do, an action word. And so when you charge something, there's some kind of action going on. What's going on? Well, in order to charge anything, there must be a transfer of electrons, not protons, electrons. So the definition of charging, to charge anything, there must be a transfer of electrons. Electrons have to move from one place to another. And so we talked about charge. And so what I want to do is continue on with the discussion. We're going to dig into this thing on voltage, and we have to introduce a couple more new terms here to understand that. Last thing about charge, remember towards the end of the session last time, we talked about 3 ways to charge an object. One way is through friction, another way is through contact, and the third way was kind of a process, kind of a long process, but it was called induction. You'll hear that word again, induction, when you get to AC if you have to take it. So we want to remember that 3 ways to charge an object. Now, I want to start with voltage first. We'll understand voltage because what you're going to understand and what you will come to realize is there's this cause and effect thing. Voltage is a cause, current is an effect. And so I want to relate these two, but to understand the effect, I first got to understand the cause. And so I want to that. But in order to get to voltage, we got to talk about a couple other terms that at first might not appear to be related, but you'll see that they're intimately related to understanding the nature of voltage, current, and resistance. The first term I want to talk about is energy. Energy. Then I want to talk about work. Energy and work. And then the third thing I want to talk about is this idea of a field. We have to understand these 3 concepts and see how these concepts are related to each other to understand the nature of voltage. And so I want to talk about these 3. So this is more, we haven't done any electrical stuff. I mean, the first module deals with just kind of the fundamentals of the basics. Some of the math stuff we'll use, like scientific notation, engineering notation, how to view a measured number. And this stuff is more about what the electrical quantities, the electrical studies, what they're based on. So this is more of a physics type thing. But it's necessary to understand the nature of voltage, current, and resistance. So let's talk about energy. What is energy? And this is the point in the class where we were meeting face to face. I would ask the question, what is energy? And I would pause, and probably nobody would raise their hand, or maybe 1 or 2 people would raise their hand. And usually the definition I get is something like this. Energy is the ability to do work. Energy is the ability to do work. And scientists might like that definition, but it's a start. So I'm going to go with that. That energy is the ability to do work. Energy is the ability to do work. Now, what we know about energy is this. We know that there's two types of it. There's two types of energy, and you might be familiar with the two types. The first type of energy is called potential energy. I'll just label it here, PE, potential energy. And the other type of energy is kinetic energy. I'll label that KE. So energy is this ability to do work, and there's two types of energy in the whole universe. There's PE and there's KE. And you might think to yourself, well, hold on a second, something. What do you mean there's two types of energy in the whole universe? There's a lot of different kind of energies in the universe. There's electrical energy, there's mechanical energy. I can go on and on and on, naming all these different types of energy, but guess what? No matter what you say, what energy you name, what type of energy you name, I can put it under the category of either potential energy or kinetic energy, because in the whole entire universe, there's only two types. There's potential energy and there's kinetic energy. So if energy is the ability to do work, what is potential energy? What is it? Well, potential energy is the energy an object has because of its position. Potential energy is the energy an object has because of its position. And let me give you an example of that, but I've got to walk away from the camera for a second and get a prop. Okay, so I have a textbook right here. This textbook has mass. And what I want to do is I want to take this textbook, I'm going to move it from here. This is my hand is my reference point. I'm going to move it from here to here. I'm going to move it up like this. Now, when I do that, I got to do something to the book to make it move from here to here. And I'll talk about that in just a second. But right now, this is my reference point. With reference to this point, my hand, right now, that book has no potential energy. In order to give this book potential energy, I got to lift the book up to here, and now it has potential energy. If I lower it back down to my reference point, there's no potential energy. If I make it twice as high, which I can't do because it'll be out of the camera frame, it'll have twice the potential energy. Also, if I raise it, let's say right here, but I double the mass, again, it would have twice the potential energy. So we know that potential energy is related to how high something is and is related to how massive something is. Now, the type of potential energy I'm talking about, you might realize that it's called gravitational potential energy. There's a gravitational potential difference between this point and when I move the book to this point. So potential energy is the energy an object has because of its position. Now let me go back. I neglected to talk about the unit for energy. Let's talk about that. The unit for energy is called a joule. A joule. So when I give potential energy to this book, there's so many joules of energy now stored in the book. It has potential energy because I raised it up. So above my reference point, there's a potential difference, a gravitational potential difference between this point and this point. And so, again, the type of potential energy we're talking about here in this case is gravitational potential energy. Well, another way to look at potential energy is the energy that an object has because of its condition. I can understand what you mean by when you say potential energy is energy it has because of its position. The higher something is, the more gravitational potential energy it has. But what do you mean when you say potential energy can also be the energy an object has because of its condition? Well, an example of that might be a spring. A spring. You might have a spring, a coil spring, and just say it's laying on the table. If that spring is laying on the table, neither stretched or compressed, it has no potential energy. But if I take the spring and I pull it out this way, I stretch it and I hold it, now it has potential energy because of its condition of being stretched or compressed. And so potential energy is energy an object has because of its position, or potential energy can be the energy an object has because of its condition, like the condition of a spring being stretched or compressed. So another way to think of this potential energy is as stored energy. This is energy that's stored in the object, in the spring because it's stretched, or in the book because it has a certain height above some reference point. Either way, it's energy that's stored. Kinetic energy is the energy an object has because of its motion. Kinetic energy is the energy of motion. The faster something moves, the more kinetic energy it has, or the more massive something is, the more kinetic energy it has. So let's look at that in a little bit more mathematical detail. You may have studied potential or kinetic energy before. You might know that the formula to calculate potential energy is that kinetic energy, Ke is 1/2 mv squared, where the m in this equation is the mass of the thing we're talking about that's moving, and this is the speed, how fast it's going. And so you can see that kinetic energy is related to the mass, kinetic energy is related to the speed, but not just related to the speed, it's related to the square of the speed. So whatever number I put in there for speed, I got to multiply it by itself. So you can think about, this a couple ways. I can have something moving really, really, really slow, but have a lot of mass, and it can have a lot of kinetic energy. Or I can have something with a tiny bit of mass, but moving really fast, and again, I can have a lot of kinetic energy. So for my first example, I might think of a glacier. A glacier is a huge piece of ice that could cover a continent, could cover land. And a glacier can literally weigh trillions and trillions and trillions of tons. Really, really massive. But it moves really slow, maybe a couple millimeters per year. Even though it's only moving a couple millimeters per year, it has a huge amount of kinetic energy because this number right here for M is so big. So the kinetic energy in a glacier that's moving a couple millimeters per year is a huge number. Or maybe I have something with a tiny mass, like a bullet. If I have a bullet has a really tiny mass, maybe it has a mass of just a couple grams, but it's moving at a really, really high speed. I don't know how many feet per second a bullet might, maybe 17, 1800 feet per second. Well, think about whatever speed that bullet is moving, however fast it's moving. Again, this is related to the square of the speed. So I got to take that number with 1700 feet per second. I got to multiply it by itself. 700 times 1700 to get this. I get I get a huge number if I square it. And even though the mass is small, again, I have a situation where I have a huge amount of kinetic energy. And so potential energy is stored in the object's position, the fact that it has position over some reference point, or energy stored in the object because of its condition, like a spring being struck and pressed, or maybe a piece of metal being bent a little bit. Either way, I have energy that's stored. And in both cases, the unit for energy is the joule. All energy has a unit of joules. Now, there's a very, very, very important and fundamental law that I'm sure everyone has heard of. It's the most famous law in all of science. It's called the conservation of energy principle. And most people understand it like this. They say energy cannot be created or destroyed. And most people can quote that. But what we actually say, the correct way to think about it is this. Energy cannot be created or destroyed. We can only change it from one form to another. Energy cannot be created or destroyed. It can only change from one form to another. Now, I'm gonna change that a little bit in just a second. But I want you to think about this now. Think about this. If there's only two types of energy, and energy can't be created or destroyed, that means that all I can have is potential energy becoming kinetic energy, or kinetic energy becoming potential energy. They go back and forth between the two. That's all I can have. Any other kind of energy you mentioned has got to be under one of those categories. So an example of that might be a swing. You might have a kid in a swing. On the prop here of a swing. So here's a swing, like at a park, like a pendulum or a swing. If I move the pendulum up like this, or the swing up like this, now it has potential energy. It has stored energy because this end of the swing is above the ground. I gave it some height. If I let it go, the potential it has is going to lose potential energy as this gets closer to my reference point. But what's going to happen is it's going to speed up. It's going to gain kinetic energy. And right here at the very bottom, when the swing is at the bottom, it'll have the most kinetic energy it can have and the least potential energy it can have. But if it keeps going, now the kinetic energy is becoming potential energy until it gets all the way over here, as high as it's going to go, and now all of my kinetic energy is converted back to potential energy. And then you know what's going to happen. That process is going to repeat. All the potential now is going to turn to kinetic. I'm going to be moving the fastest down here that I'm moving, so I got the maximum amount of kinetic energy. And when I get back over here, all my kinetic energy is turned to potential. Now I have all the potential and no kinetic, and it's going to keep going. Ideally, it's going to go back and forth and oscillate between PE and KE, PE and KE. So energy cannot be created or destroyed. It can only be changed from one form to another. Well, we got one more term to look at. Is this idea of work. I can see that energy is the ability to do, we got the word right there, work. It's the ability to do work. So, all right, if energy is the ability to do work, what is work? And I want to ask a question that if I have this is a textbook, it's fairly heavy. I'm just going to hold this book like this. I'm going to hold this book like this for a really, really, really long time. I'm going to hold the book like this, say, for some hours, and my arm's going to get really tired. And if you ask the person holding the book, are they doing any work? And they're probably going to say, yeah, I'm doing a lot of work. My arm's getting really tired when I put this book down. But if you ask a scientist or engineer, is that person doing work? They'll say, nope, they're not doing any work. Why? Well, in order for work to happen, in order for work to be done, two things have to happen. Work, you got to have a force. In order for work to be done, you got to have a force. Well, actually, I have two forces here. I got a force. There's a force of the book on my hands pushing down that way. That's the weight of the book. And there's a force of my hand on the book. So we got this. We got force. But we're still not doing any work, because the second thing we need to say we're doing work is that force has to make something move through a distance. That force has to cause the object to move through a distance. So the reason I can say that I can hold this book, and no matter how tired I'm getting, I'm not doing any work, is because the book has not moved. In order for me to do work, I actually got to move the book like this. Now I'm doing work. I'm doing the work as a force acting through a distance. I'm doing the work of moving the book from point A to point B. So make sure you have that clear in your mind. Energy is the ability to do work, but for work to happen, there has to be a force And that force has to make something move through a distance. And so there's got to be motion. So anytime there's motion, that brings in this idea of kinetic energy because that's related to motion. Well, let me back up for a minute and let's go back over here. We mentioned the fact that there's two kinds of energies, only two kinds in the whole universe, potential and kinetic. Potential energy is stored energy. Kinetic energy is energy of motion. And we mentioned the fact that the unit for energy is the joule. But what is the unit for work? You might be surprised to learn that the unit for work is the joule. We might say, well, hold on a second. Are you saying that I have these two different physical quantities, but yet they share the same unit? And I'll say, yes, that's exactly what I'm saying. If you have energy, its units are joules. If you have work, its units are joules. And the reason is the idea of energy and work are so intimately related that the scientists give them the same unit. And that's the only physical quantity that I can think of where you have these different physical quantities sharing one unit because they're just basically two sides of the same coin. And so it's important to know that there's energy, there's work, and under energy, there's two kinds. There's PE, KE, and each one of those, whether I'm dealing with work, energy, potential energy, kinetic energy, it's all measured in joules. The unit is the joule. So I want to go back. I mentioned to you the conservation of energy principle. Energy cannot be created or destroyed. We can only change it from one form to another. I want to say that another way. Instead of saying energy cannot be created or destroyed, I want to say joules. Joules cannot be created or destroyed. If you have a certain amount of joules of energy, whether PE or KE, or if you have a certain amount of number of joules of work, they disappear. When something is conserved, energy is conserved, I'm going to say joules are conserved. And that means that whatever amount of joules you start with, you got to end up with that same amount. You got to be able to account for it. So let me explain that like this. Let's go back to my example of the book. And my hand is my reference point. And what I want to do is give this book potential energy. Well, anytime you measure a potential difference, you got to have 2 points. You got to have a reference point, and you got to have the point to where we're moving this object to. And the difference in energy between the where we're moving it to and where it came from is what we call a potential difference. In this case, a gravitational potential difference. So let me do this. I want to relate energy, PE, energy, KE, and work all together. Let's see how this interaction is. So what I want to do is give this gravitational potential energy. And so what I got to do is I got to lift this from here to here. But what do I got to do to lift it from here to here? I got to do work. I got to do the work. I got to work. Here's a force acting through a distance now. So I do the work of moving the book from here to here, and now that book has potential energy stored in it. But let's go back and think about what I just did. I did work. There was a force on the book, and I moved the book up through a distance. So I did work. I did so many joules of work. Remember what I said. Joules can't just disappear. Joules can't be created or destroyed. All I can do is change it from one type to another. I can change it from joules of PE, joules of KE, or joules of work. So in this case, what happened is this. I have the book there. I wanted it 10 joules of potential energy. So what do I have to do? Well, I got to do 10 joules of work. There's a force acting through a distance to push this book up to this position. And let's say I did 10 joules of work in moving the book from this point to this point. Those 10 joules can't just disappear. Those 10 joules are conserved. So where are they now? Those 10 joules of work are now stored in the book as potential energy. If I want to get those 10 joules out, all I got to do is let the book go. When I let the book go, the book will, for a second, just kind of float there, all potential energy, but then it'll start to fall. As it's falling, the potential energy is decreasing, But since it's moving faster and faster as it starts to fall, the kinetic energy is increasing. And so it's going from all potential to all kinetic energy of motion. And right before it strikes the ground, 10 joules of potential energy is now 10 joules of kinetic energy. And so if you can relate those three, that's extremely important. So again, what I had to do, I had to first make a gravitational potential difference. I got to do work on the book, separating it from my reference point up to this position. The joules of work that I've done is now stored in the book as potential energy, not work anymore, but potential energy. It has the ability to do work, but it ain't no work. If I want to get the joules out of it, I'll let it go, and then it'll start to fall. As it's falling, since the height is decreasing, the potential energy is decreasing, but in the exact rate that the potential energy is decreasing, that's how fast the kinetic energy is increasing. And as this speeds up, right before it hits the ground, right before it hits my reference point, all the PE has become KE. And so you can see why I said what I said about stating the conservation of energy principle a different way. Instead of saying energy cannot be destroyed, joules have to be conserved. Joules can't be created. Joules can't be destroyed. All the joules have to count. In the end, when something happens, I got to be able to add up all the joules that I started with, and they got to equal all the joules that I end with. So this relationship between potential energy, kinetic energy, and work is critical to understanding the nature of voltage. Now, remember, no work takes place if something doesn't move. There cannot be any work without motion. So in order for there to be work, something's got to move. Well, let's do it one more time, because what you're going to see is we can go around a circle. What do I mean by go around a circle? Well, I'm going to start with my book on my reference point. I'm going to do some work on the book. Let's say I do 10 joules of work book, moving it from here to here. So I've done 10 joules of work. So now those joules have went from joules of work to joules of potential energy. The energy is stored in the book as gravitational potential energy. And now I want to get the book out. I want to get the joules out. So I let this go. And as I let it go, now this is motion, it's moving. The PE is decreasing, the KE is increasing as it speeds up. Right before it strikes the ground, I have all KE. I have 10 joules of KE. And now the KE, let's say this was a driver, and I have a stake. I want to knock it in the ground. The KE can actually do the work of knocking a stick into the ground. It can cause a force to cause something to move. And so I started with work. I changed those joules of work to joules of PE, and from joules of PE to joules of KE, and KE is the only type of energy that can do work. So again, all joules are conserved. Now, I want to go on, but there's one more term I got to pull into this to understand voltage, and that's this idea of a field. Does anybody have any questions so far about what I've talked about? This is really, really important. So I want to make sure it's crystal clear. Any questions or comments over anything I've talked about so far? Okay. Well, let me go in there. I want to get to this idea of a field, but let's make sure we understand the terms, the terms we're using. So one term that we started with was energy. And we said energy is the ability to do work, either work being done or the ability to do that work. We know there's two types of energy. There's potential energy and there's kinetic energy. We said that the potential energy is energy an object has because of position or condition, and that in order for an object to have kinetic energy, it's got to be moving. Kinetic energy is the energy of motion. And then we talked about work. We said work is what happens on an object. You can do work on the object if there's a force on that object and that object is moving through a distance. If that force is causing the object to move. Well, anytime something moves, you're relating it to that, right? That means it has kinetic energy. And so work can cause kinetic energy, and kinetic energy can cause work. And so we talked about that. So for work to happen, there must be a force, and that force must act through a distance. So my next question is this. It looks like work is related to force, but what is force? What is force? How do you think about force? And one of my favorite people is Albert Einstein, and one of the things that he taught was that when you're explaining the concept to somebody, he said if you can't explain it to a child, you don't know what you're talking about. You don't know it well enough yourself. So I want you to think for a second. These concepts we're talking about, specifically I want you to think about force. How would you explain the term force to a kid? How would you explain it in the simplest words to a kid? And since I don't have the luxury of you guys raising your hands and telling me about it, I'll give you the way I would say it. I would tell the kid a force is a push or a pull. A force is a push or a pull. And there was a physicist named Isaac Newton that taught us a lot about forces, and I won't go into a lot of what he says, but he did have this law, Newton's third law. Newton's third law, and people say it the wrong way. Newton's third law, a lot of people say for every action, there's an equal and opposite reaction, and that's kind of right, but what he actually said was for every action force, there's an equal and opposite reaction force. In other words, what Newton was telling us was it's impossible to have one force. There's always at least two forces. There's a force you call an action force. There's a force you call a reaction force. So, for example, well, I'll just put my hand here on the board. If I push on this board, there's actually two forces according to Newton. And there is. There's two forces. And right now I'm pushing on the board. What I know is the board's pushing back. Well, how can you say that? The board's pushing back. Well, think about it. If I was pushing on the board this way with 10 pounds of force and the board wasn't pushing back, or if it was pushing back with, let's say, less force, like 3 pounds of force, I would go through the board with 7 pounds of force. If I reverse that, if the board was pushing back on my hand with 10 pounds of force, and my hand was only pushing at the board with 3 pounds of force, I would go moving towards the camera with 7 pounds of force. But the fact that I'm pushing on the board and I'm not moving and the board is not moving means that whatever amount of force I'm pushing on the board with, the board has to be pushing back. Those are the two forces I'm talking about. There's the force of the board on my hand, that's number one, and there's the force, I said that wrong. There's a force of my hand on the board, and there's a force of the board on my hand. Two forces. And so one of the things Newton teaches us is this idea of forces. Forces exist in pairs. A force is a push or pull. What I want to get to about forces is a little bit more interesting than that. Let's talk about forces. It turns out in nature, there's two kinds of forces. I should say two categories of forces, not two kinds. There's two categories of forces. So force the first category is called a contact force. The second category has a long name. It's called an action at a distance. Force. So the contact force is the easiest to understand because we observe observe it all the time. So let's talk about a contact force. What is a contact force? Well, a contact force is just what the words imply. One object exerts a force on another object because they're in contact with each other. They're touching. And so if I use this eraser and I'm going to apply a force on the eraser, my hand is touching the eraser. I'm about to push it. So my finger is applying the force to the eraser. And according to Newton, since I got to have two forces, the eraser is applying a force to my finger. And actually, there's another force there, the force of friction, but we won't get into that. But you can see that if I'm touching the eraser, I can actually force the eraser to move. The two objects, my finger and the eraser, are touching each other. So I can have a transfer of force, or I can do work, right? If I have a force acting through a distance, there's a force acting through a distance. I can think of this as a transfer of a force or transfer of energy. I'm giving energy. I'm doing work or kinetic energy on this as I move it because I have a force and the two objects touch each other. So one type or one category of forces is a contact force. The two objects touch each other, and in touching each other, I can make something move and I can do work on the object, but the two objects have to touch each other. And that's cool. But here's the one that's really interesting. This is called an action at a distance force. What is an action at a distance force? Well, let's go back to my contact force. Imagine that instead of having to do this, instead of having to have the two objects touch each other to apply a force to make it move, is it possible for me to just get close to the object, never touch it, never come in contact with it, but to have this move away or move toward it? And if you think about it long enough, you will say yes. That happens in three ways. There's three types of action at a distance forces that I know about. The one that most people know about is called magnetism. So I can have magnetic forces. I can have a magnet. You've all played with magnets before. You know this. If I have a North Pole and a North Pole, say I have these two magnets sitting on a very smooth surface and they're really strong magnets, and I do this. I start to move one magnet towards another. If I have like poles facing each other, a north and a north, they never have to touch. This magnet can actually push the other one away because the magnetic field is repelling it. It's pushing it away. And so I can actually cause work to be done, but the two forces, the force causing the work to be done, they never have to touch the other object. I can get close. This can move away. That's a force acting through a distance. That's an action at a distance force. So one of these types of action at a distance forces are magnetic forces that you're all familiar with because you've all played with magnets before. Well, here's another one you're familiar with: gravity. Gravity, the force of gravity is an action at a distance force. And so if I lift the book up, I let it go, you know it's going to fall. If you ask a kid why, he might say because that's down, but there is no down because we live on a sphere. The earth's a sphere, so there is no up or down. The reason the book moves is because the earth is pulling down on the book. It's a gravitational force of attraction, the book to the earth. But remember, Newton says you can't have one force, you got to have two. So if the earth is pulling down on the book is also pulling up on the earth. The earth has mass, the book has mass. Anything that has mass is attracted to anything else that has mass through gravity. And so, again, I have an action at a distance force. Let this go, the force of gravity is going to pull the book down. The force of the book can't pull the earth up. Obviously, the earth is too massive, but the earth can pull the book down. Again, the force of gravity, action at a distant force. The earth never had to touch the book in order for that force to be transferred from the book to the earth, or vice versa. and the magnets never have to touch each other in order for one to apply a force on the other magnet, action at a distance force. So most people, if you remember, you might not have thought about it like this and gave it that name, but most people kind of know this. You know that magnetic forces are action at a distance forces because of experience. You play with magnets. We've all experienced gravity. If you jump off of a building, you know the law of gravity. There's a force that's going to pull you down. But there's a third type of action at a distance force that most people are not familiar with, but if scientists or engineer, you probably are. There's magnetic forces, there's gravitational forces, but the other type of action at a distance force is called electrical force. I'm going to put that up high here, because that's the one we're going to talk about, the electrical force. Now, in physics, that has another name. They also call it Coulomb force. So Coulomb force and electrical force are the same. But here's how it works. If I have objects that have charge, now I'm using charge as a noun. If I have a plus charge and a plus charge, you know, like charges repel. And so if I start to, let's say this is charge 1 and this is charge 2. If I start to move charge 1 towards charge 2, charge 1 and charge 2 never have to touch each other. Charge 2, if I get this close enough, is going to move away because like charges repel. Charge 1 is going to exert a force on charge 2 to cause it to move, which means it now has kinetic energy and this is doing work. But the idea is they never ever have to touch each other. And so the electric force or the Coulomb force is another type of action at a distance force. So there's 3 of them that we know about. Magnetic forces, action at a distance force. Gravitational forces, action at a distance force. And the one that we want to focus on, electrical forces, Coulomb forces, action at a distance force. Now, what do all 3 of these have in common? There's one thing that all 3 of these action at a distance forces have in common, and I've already mentioned it today. The one thing they all have in common is they all have a field. There's a magnetic field between 2 magnets. You may have done the experiment in high school or junior high school where you take a magnet and you take a piece of paper and put over the magnet, and then you get some metal shavings or filings, and you just like almost the size of a salt or pepper shaker. You get these little, basically magnetic powder, and you sprinkle it onto the paper and you move it around, and you can actually see the magnetic field caused by a magnet. If you've never seen that before, don't do it now, but maybe sometime today, YouTube, just Google magnetic, just Google magnetic field of a bar magnet, and you can see people doing experiments. But the point is, we know when you play with magnets, we know there's something there because you can kind of flip. I got a North Pole and the North Pole. You can't see it, but you can experience. You know the field is real. It's living. It's alive because you can experience. You know there's something going on when you try to push them together. So there's a magnetic field. There's also a gravitational field. I can feel the weight of the book. The Earth's pulling down on it, so this book has weight. But if I took this to, let's say I went in a rocket ship and I took it out of orbit of off the Earth, get far enough into space, I wouldn't feel the pull of the Earth anymore because I would have escaped the Earth's gravitational field. It's not pulling down on it anymore, so it doesn't have any weight. You know that when astronauts go to space, they're weightless. What does that mean to be weightless? It means that the Earth's not pulling down on them anymore, so they're weightless. So we've experienced this. We know that there's a gravitational field. And you haven't really experienced electrical fields or the electric field, but you can imagine how they work because they're very similar to magnets. You know, if I have a magnet, if I have a north and a north and try to push them together, they're going to repel. If I have a south and the south, push them together, they're going to repel. If the poles are the same, they're going to repel. If I have a north and a south, they're going to attract. Well, charge works the same way. If I have a plus and a plus, they're going to repel. If I have a minus and a minus, they're going to repel. If I have a plus and a minus, then these two are going to want to come together. But again, if I have a plus and a plus, I can take this Q1, move it towards Q2 without ever touching it, and Q2 will feel the force of repulsion from Q1. It'll move that way. Act of the distance force. So this idea of a field, all of these have fields. What is a field? Well, that's the next term I want to deal with, but unfortunately, I can't answer that. We don't know. We don't know exactly what a field is. In science, we have two types of definitions. In science, we have a regular definition that says what something is. Sometimes in science, we can't say what something is. Like I don't know. I can't tell you what energy is. I can't tell you what charge is. We know that energy exists, and we know there's two types. We know that charge exists, and there's two types, but I can't really tell you what it is. And so in science and engineering, if we can't say what something is, we define it in terms of what it does. That's called an operational definition. And that's actually very important. It's a simple idea, but it's important because it allows us to move on with our thinking. We don't have to worry about, you don't have to get stuck on what something is if we define it in terms of what it does. And so an operational definition of a field. We don't know what it is. I can't tell you what it is. I can tell you what it does. It will transfer forces. A field is a mechanism in space that transfers force or energy. Or I should say force and energy, because if you transfer force, then automatically you're transferring energy. So we can't really say what it is, but this is region. If I have these two charges here, and they're stationary, and I start to move Q1 towards Q2, well, Q2 is going to feel the force of repulsion from Q1. So some kind of way, that force is going from Q1 to Q2. They're not touching each other, so it's got to be an action of the distance force. The way it's doing that, it's moving through the field. So the field can transfer force. Well, a field can also transfer energy because, think about it, if this charge is stationary and this charge is stationary, if I start to move Q1, start towards Q2, the force of attraction eventually is going to push Q2 away. And if that force, I said force of attraction, I meant repulsion. There's a force of repulsion between Q1 and Q2. If I get close enough to Q2 with Q1, the force of repulsion from Q1 on Q2 is going to cause Q2 to move away. And if Q2 was originally stationary and now it's moving, that means that I've done work on Q2. I'm causing Q2 to move. I'm giving it kinetic energy. So I can transfer force through the field and also transfer energy through a field. Anytime you have a field, you can cause energy to move through that field. You can cause force to move through the field. Actually, you do the two together. And so this turns out to be really important because let me tell you why. What we want to do is we want to make an electric current. Now, one of the things you want to understand, what is electric current? I'm just going to tell you right now what it is. Electric current is charge in motion. Specifically, electric current is electrons in motion. Electrons are always in motion. You know that they're in motion around the atom. They're spinning around the atom. They're revolving around the atom. We talked about that. Sometimes you have an electron fly off of the nucleus and move around, and an object randomly just kind of fly off. So electrons are never stationary. They always have motion. Electrons are always vibrating. They're always moving. But to have a current, you have to have electrons. They have to have motion. All the motion has to be the same way. So there has to be a net motion, a net flow of charge in one direction in order to have a current. Well, how do you take something that's kind of stationary and make it move? Well, the way you do that is you apply force. You apply force to something, you can make it move. Well, I want to make electrons move, so I can't apply this kind of force. It's silly. I can't put my finger on an electron, push them. I can't push electrons to make them move, but we can make the electrons move like this. An action at a distance force can exert force on electrons to make them move. So the nature of current, what current is charge in motion. Most of the time, it's electrons that is the charge we're talking about. So we're going to call electric current the movement of electrons. So I got to take electrons. I got to have some, like a group of electrons, in some kind of way, I got to make them move. And that's what I want to talk about next. So we talked about a lot here. You got to make sure you're clear on energy and work. You got to make sure you understand that there's two kinds of energy, potential and kinetic. And then when you relate work to that, that all of those quantities, potential energy, kinetic energy, and work, all share the same unit because they're so closely related, we give it the joule. And I mentioned that all joules are conserved. So I can do work on something and give that something potential energy. I can release the potential energy by, let's say, dropping it or letting the spring go. And that's going to cause something to move. So now we have kinetic energy. And if something's moving, it can do work on something else. It can, if I have a brick that's falling, it can do the work of hammering a stick into some mud or into the ground. So this idea of work and energy is important. And then when we bring force into the fold, we talk about forces. We know there's contact forces, things are touching. But for us, what's important is this action at a distance force. There are at least three quantities in nature that we know about where I can have one object exert a force on another object, but yet the two never have to touch. And in three cases, one case was magnetic forces, second case, gravitational forces, but the one that's important for us is electrical forces. Anytime I have charge, there's a field around it called an electric field. Anytime I have something that has mass, there's a field around it called a gravitational field. And anytime I have something that's magnetic, there's a field around it called the magnetic field. And what I want to do is talk about the electric field. So now we're dealing with things that are really, really abstract, but you just kind of use your mind's eye to kind of visualize this stuff. So let's talk about the electric field. So if I have plus charge and minus charge, in the region between these, I have the electric field, which I draw coming from the positive charge and going to the negative charge. So one of the things to understand is that the electric field has direction. It has direction. And so when I draw the electric field, I'll draw it like that. So these lines of electric field or lines of electric force, they never cross each other. And if I have a positive charge, notice the field is coming out of the positive charge and going to the negative charge. And if these are free to move, there's going to be a force of attraction for these two. The two are going to pull towards each other and they will come together. And the way that force is being transferred from one object to the other is through the electric field. The other thing to know is if I have these two charges, or think about let's go to magnets. We've all played with magnets. Say I have a north pole and a south pole, and I know if I get them close enough, they're going to stick. If I hold them close together, but I don't let them come together, I can feel the strength of the two magnets wanting to come together. And so I can feel a certain amount of attractive forces between these. So the magnetic field, which looks like this, but you can't see it, it's wanting to pull these together. Well, I realized through experience that if I make this gap bigger and bigger and bigger, that force of attraction between the two decreases to the point to where if I get these far enough apart, I can't even feel them wanting to get together anymore. And it's the same here. The further these are apart, the weaker the field. The further apart they are, the weaker the field. And that's true of any kind of field, whether it's a magnetic field, a gravitational field, or an electric field. When I fire a rocket ship on Earth, in the beginning, the rocket is heavy and it uses a lot of fuel and it's going slow. It's trying to escape the Earth's gravitational field, but then it gets high enough, it moves faster, it's burned off fuel, and the Earth's pull on it is lessened, reduced. The further it gets away from ground, the easier it is to move because the field, the strength of the field, the force between the Earth and the rocket that's transferred through that gravitational field is greatly reduced to the point to where when it leaves the Earth's atmosphere, there's hardly any pull from the Earth's gravitational field. So this idea of a field is very, very, very important. So let me now relate this to voltage, because all comes into play. So now I'm going to answer the question, what is voltage? So to understand what voltage is, what I have to do is start with charge. Now I'm going to start with now just single charges, but remember, I don't have just one positive and one negative. I'm only doing it this way because it's easy for me to show, but I'll show you here in a second how we really think about this. But let's say I have two charges, plus charge and minus charge. That's very similar to the situation of having two masses. When I got my hand, so that's the ground, that's one mass, and the book is another mass. Having two charges sitting on top of each other, it's like having two masses sitting on top of each other. And if I want to separate these two masses, what I want to do is I got to do some work. Work is forced back into a distance, so I got to do work separating the book from the Earth. So I got to do work. And whatever amount of work that I do is now stored in the book as potential energy. I would say that there's a gravitational potential difference between this point and this point, and then that gravitational potential energy is stored energy. Well, I can do exactly the same thing here. I can separate these. Now remember, unlike charges attract each other, so these are stuck together. So if I want to separate these, it's going to take some effort on my part. I got to do some work. And even when I get them separated, let's say that when they're like this, when I get them separated, they're still going to want to come together because they're so close, the field is so strong, I got to hold them apart. So I got to do work to separate the two charges. But eventually, I can do the work of separating them. And when I have them separated now, they actually have potential energy. But not this kind of potential energy. Here, the thing that will pull them back together is gravity. So it's a gravitational potential difference between this point and this point. Here, the thing that wants to pull them together is the electric field. So there's not a gravitational potential difference between this point and this point. There's an electrical PE stands for potential difference. An electric potential difference between these 2 points. If I separate charge, so if I separate masses, I get a gravitational potential difference. If I separate charge, I get an electrical potential difference. For voltage. If I separate charge, I get an electrical potential difference or voltage. And so just because there's distance between these two charges, I have an electrical potential difference, but I just call that voltage. Oh, hold on a second. So am I saying that voltage is just a separation of charge? And the answer is yes, excuse me. If I want to make a voltage, all I got to do is separate charge. Again, I'm showing one single charge. We don't deal with single charges, we deal with groups of charges. But by definition, all a voltage is an electrical potential difference, separated charge. Anything that creates a voltage, what it's doing is separating charge. Batteries separate charge. You know that one terminal of a battery is marked positive, the other terminal is marked negative for a reason, because through electrochemical action, what the battery is doing is separating charge, making one terminal missing, there's missing electrons, and the other one has an excess of electrons. It's a separation of charge. There's a voltage between the two terminals. If you have you plug something in the wall, there's a voltage there. Most of you know it's 120 volts, but that voltage is not coming from a battery, it's coming from a generator. So generators separate charge, not the way a battery does. A battery does it through electrochemical action. A generator does it through electromechanical forces. And we'll actually talk about that. For AC, we're going to understand how the generator does that. How does the generator separate charge? How does the generator create a voltage? Another way to create voltage is through you might have a solar panel or solar cell. Einstein discovered something called the photoelectric effect, where if conditions are right, you think of light as a little particle of light that hit an electron and separate from the atom, and I have, again, a separation of charge. No matter what, if you see the word voltage, that means the thing that you're applying it to, what it's doing, some kind of way, is separating charge. So our definition of voltage is a separation of charge. Well, let me give you a little bit better definition, and if you're doing the quiz, this is actually important for the quiz. Let's say I have a group of charges. Normally, we don't deal with just these point charges. We don't deal with single charge. So let's say I have a bunch of charge right here. So I got negative charge here. And down here, I got positive charge. So I got a bunch of charge, separated charge. Some kind of way I separate it. What I do is take some more charge. So I got some charge here. Now this is negative charge. That's 1 coulomb. 1 coulomb. 1 coulomb of negative charge. Now, you see how close that is to that? Unlike charges are going to attract, so those electrons are going to want to go down here, right? Well, I don't want them to. What I want to do is I want to push them. I want to push them up here. I want to move them up here. Light charges repel, so I got to do a lot of work to get this 1 coulomb of charge up to this group of negative charges that I have up at the top. I got to do work because light charges repel. Well, let's say I do 1 joule of work. I'm trying to move these up, so I'm exerting 1 joule of energy. I do 1 joule of work in moving 1 coulomb of charge through a distance. Then I would say I have 1 volt of potential difference. If I move 1 coulomb of charge, if I exert or use 1 joule of energy, moving 1 coulomb of charge to a distance, then I have 1 volt of potential difference. And so another way to think about a volt, the units, 1 volt equals 1 joule per coulomb. Let's say I have, I don't know, I was going to give you a quick example. Let's say I have 2 coulombs here of charge, and I'm gonna push this way. So I got to force this up there, and I use 5 joules of energy. I exert 5 joules of energy. I use 5 joules of work moving this 2 coulombs of charge from here up to the top. And I will say voltage equals work per unit charge, and the work I've exerted 5 joules of work or energy, however you want to say it. I've used 5 joules of work to move 2 coulombs of charge. If I divide that, I get 2.5 joules per coulomb. I'll call that 2.5 volts, potential difference. And so you know your car battery is 12 volts. That means 12 joules per coulomb, or 12 joules per coulomb. So this formula right here is important for quiz 2. Understanding quiz 2, and there should be an E here. So voltage is a separation of charge. Any device that separates charge creates voltage. The main way we do that, at least for this class, is through a battery. Batteries separate charge, therefore batteries create voltage. Any questions? Okay, so you know the answer to this now. It took a long time to get there. But if I ask you what is voltage, your answer is going to be voltage is a separation of charge. We don't really care how the charge got separated. If you want to know that, if you want to know how batteries work, you got to take a chemistry class. We'll talk a little bit about it in AC if you want to know how generators work. But all we know is we don't really care how it separates the charge. But anytime charge is separated, it creates a voltage. Whether on purpose or not, anytime charge is separated, it creates a voltage. So voltage is a separation of charge. Now what is current? Well, I've already answered that question. I told you, current is charge in motion. When we talk about any kind of current, think about it. Let's say I have air, the air sitting in the room not moving. We don't really talk about air current. If I put a fan in the window and cause the air to move, then I can feel the current from the air. The wind is air current. It's air molecules in motion. It's improper to talk about air current if the air isn't moving. The same with water. If I have water in a lake, but the water's not flowing, it's just sitting there. If I have water in a puddle, we don't talk about water current. But if I can some kind of way make the water flow in a stream or a river, now I have a flow of water. I can have a flow of air to make an air current. I can have a flow of water to make a water current. I can have a flow of charge to make an electrical current. Now there's 2 kinds of charges. There's plus charge and there's minus charge. More often than not, we're moving electrons because the positive charges are in the nucleus of the atom. We usually don't have access to positive charges. But if I did, it wouldn't matter. I can move either the electron or the proton. Either way, if I have charge moving, I have an electric current. We're going to focus on electrons. So that's easy to answer. It's very easy to answer. Current is electrons in motion. Current is charge in motion. A harder question to answer is, okay, well, how do I get them to move? It's not that they have to move. Electrons are always moving. I got to make them all move, and I got to make them move in the same direction. So a better question would be, what can cause an electron to move? And let me show you how we do it. It turns out that if I want to make something move, what I got to do is put a force on it. Well, it's impossible to use a contact force. I can't touch an electron to make it move. But here's what I can do. Suppose I had some charge. I got a bunch of charge. and I separate it. I got some charge like this, and I got some negative charge somewhere else. And I separate this charge so it looks like this. Well, if I separated this charge so it looks like this, then what I have is an electrical potential difference or voltage. If I separate the charge, now I have a voltage, an electrical potential difference from here to here. There's a voltage. But not only is there a voltage, as I mentioned before, anytime we have separated charge, in this region of separated charge, you also have electric field. So that represents the electric field. Now, let me take one electron, even though I say we don't work with one electron. I'm going to take one electron and put right here. Just one electron. I put it in this voltage. I put it in this potential difference. If I hold it there, I'm going to notice something. I'm going to notice that that electron really wants to move that way. Why does the electron want to move that way? Well, the reason is, earlier we said, think about the law of charge. Like charges repel, unlike charges attract. And so right here, this group of negative charge is pushing this away from it, while at the same time, the group of positive charge is pulling it towards it. It's going to want to move that way. There's a force wanting to move that way. Law of charge. How does the force get from here to there, or from here to here? Through the electric field. The electric field can carry forces. The electric field carries the force of repulsion from this negative charge to here, and at the same time, the electric field carries the force of attraction of the positive charges here and that negative charge. Either way, it's going to want to move that way. Now, I want to be very precise in my language right now. I separated charge and caused a voltage, a potential difference, an electrical potential difference. And now, when I put a charge in there that's free to move, it's going to feel a force, and that force is going to want to make it move up that way. And the force that it feels has a name. This upward force right here has a name. Let me erase this. It's called electromotive force. Electromotive force. The electromotive force is a force that a free electron will feel when you put it in a magnetic field. This is the force it experiences when you stick it in that electric field. I said magnetic, I mean electric. So this is called an EMF, electromotive force, EMF. So you can imagine, if I go back, let me go back to my other example. Instead of having one electron in the field, in the electric field, what if I have a group of electrons in the electric field? So I have 1 coulomb of electrons, 1 coulomb of charge. And let's just say that I'm looking at this. So here's my eyeball. This is my eyeball. And I'm looking right here. I'm looking at this charge move this way. So while I'm on a charge, if I see 1 coulomb of charge move past a point in 1 second, then I say I have 1 amp of electric current. So in other words, current is coulombs per second. How much charge moves past a certain point every second gives us the flow of current, the flow of charge. And so let me write that as an equation. And again, this will help you with quiz 2. We use the symbol I for current. Now I'm going to use a lowercase I for current because that uppercase is going to mean something else. But let me write it out first so you'll have it. I'll write it like this. So current is charge per unit time. Is the formula. And remember that this is in coulombs, and that's always in seconds. So you can see my units here are coulombs per second. So we're going to write it like this. For current, we'll use an I. We use a lowercase I for now, but eventually it'll be an uppercase I. So I equals charge. We use a Q for charge, and we use a lowercase t for time. So you want to make sure you understand there's a cause and relationship between current and voltage. Voltage causes current. Over here, what I had to do, I first took the charge that was together and I had to separate it. I had to create a potential difference, an electrical potential difference. I had to create a voltage. And once I separate it, then in between, in that region of separation, I have an electric field. And then when I insert an electron or charge in that electric field that's free to move, it's going to experience a force, an electromotive force, that causes the electron, a group of electrons, to move from the negative to the positive. So that's important. So notice the voltage, it took a voltage to create a current. So cause and effect. Voltage is the cause. The effect of a voltage is current if those electrons in that potential difference are free to move. And then I gave you the formula for current. Current is charge per unit time. I also gave you the formula for voltage. Voltage is work per unit charge. Now on the practice sheet, if you have it, I think we worked 3 problems on that practice sheet. One was we had to determine if copper was an insulator, semiconductor, or conductor. So I think we did that example. There was a couple other on there where we had to convert so many coulombs to electrons and so many electrons to coulomb. I think we've done that. But there's another one where we're given 5 coulombs of charge, and it moves past the point. I think in, I want to say 0.5 seconds. I don't have the paper in front of me. I think that's what we say, that we have 5 coulomb of charge is made to move past the point in 0.5 seconds. How much current is that? So if you were going to do that, you just, I got 5 coulombs. Q is 5 coulombs. My time is 0.5 seconds. And so my current is going to be 5 coulombs every second, 5 coulombs a second. But 1 coulomb per second, we call that 1 amp. An amp is short for ampere. So we say that this was 5 amps of current. 5 amps. So these formulas right here are important. Write this down if you're taking notes. And when you look at quiz 2, then you'll need that for some problems on quiz 2. So with this, you should be able to do everything on quiz 2. And I believe it's due to, I want to say it's due tonight at midnight. You guys check it out. But if it is, make sure you write this down, and you can use that. And this should solve out everything we've talked about so far should allow you to work quiz 2. So we've done a lot here. We've understood this idea of voltage. I want to make a voltage, I got to have something to separate charge. Once I have the charge separated, I have electrical potential difference or voltage. And in that region of the potential difference, I will have an electric field. And that electric field, if I have charge is free to move, the electric field can cause the charge to move from the negative to the positive. Notice that the charge moves from negative to positive, so the direction of current flow, the actual direction of current flow is from negative to positive. We'll talk about that another time, but that turns out to be kind of important. Any questions? We went through a lot. Any questions? This is some deep stuff, but you just got to kind of think about this for a while and let it kind of sink in, and hopefully this makes sense to you. Anybody have any questions over voltage, or do you have any questions over charge, or anything we did so far? And if you don't, I want to move on to resistance, and we'll be finished with the big three, what I call the big three. So any question on voltage or current? Well, the last thing I want to talk about is resistance. Resistance. Resistance is the opposition to current flow. Resistance is the opposition to current flow. Well, okay, that's nice to know, but how? I mean, where does that opposition come from? Well, that's what I want to talk about. The other thing I want you to think of resistance as, think of resistance as the electrical equivalent to friction. Resistance is the electrical equivalent to friction. What is friction? Well, friction is kind of complicated, but basically, friction is the force that opposes motion. And so you might think of it like this. Let's say I have a bowling ball or a soccer ball or something, and I'll roll it down the hallway. When it gets to the end of the hallway, it hits the wall, it's going to stop. But let's say I have a hallway with no end. I have an infinitely long hallway. There's nothing for it to run into. And I take the bowling ball or the basketball or the soccer ball and I roll it down the hallway as hard as I can. It's going to move, but eventually, after a while, that ball's going to stop. Even though nobody touched it, it's going to stop. Well, what stopped it? What stopped it was friction. Friction opposes motion. So some of that kinetic energy that I gave the ball initially to make it move is rolling down. The frictional forces oppose that motion, and some of that motion, remember, energy can't be created or destroyed. It's got to go somewhere. Some of that motion is dissipated as heat. Anytime there's frictional forces, there's heat associated with it. So the speed of the ball is going to slow down, but the heat that's created, because it's slowing down, it's got to be exactly related to how much energy the ball is losing. Eventually, the ball stops. All motion and friction would have dissipated all that energy of motion as heat. Well, it turns out resistance is exactly the same way in that it produces heat. Resistance always produces heat. Friction always produces heat. And that's why I say that you think of resistance as your electrical equivalent of friction. Is friction good or bad? And the answer is, I don't know. It depends on what we're doing. Friction could be bad. It's bad in your engine. You put oil in your engine because you want to reduce friction. But it's good if you're trying to get traction on your tires. And in the wintertime, when there's a lot of ice, you might put sand down to give you some traction if you get stuck. So is friction good or bad? Depends on what we're doing. Resistance is the same way. Resistance is sometimes good. Resistance is sometimes bad. It turns out for us, what we want to do with current is control it. And one way we can control current is by using resistance. We'll talk about that at a later date. So resistance is the opposition to current flow, and resistance always produces, let me put that on the board, always produces heat. I'm going to say just like that's why I say resistance is the electrical equivalent of friction, because it always produces heat. So when you plug your cell phone charger in the wall, you put your hand on the charger, you feel it's a little bit warm. That's because of the resistance in that charger. That's what you're feeling, the heat due to resistance. Okay, resistance is the opposition to current flow, but where does that opposition come from? What causes the opposition? And that's what I want to talk about next. And to understand that, let me do this. I'm going to draw a copper wire. I'm going to make a really big copper wire like this. So that's a copper wire. Now let's go back and talk about copper a little bit more. We talked about copper already. Here's what we learned. We know that the atomic number for copper is 29. So if its atomic number is 29, we know that it has 29 protons, and if we assume we have a neutral atom, we have 29 electrons. So a neutral atom of copper, 29 electrons. And if you remember, when we did that shell capacity calculation, we did it with copper, and we placed those electrons in the orbits. If you remember, what we had in copper was we had a nucleus plus 29, right? But then these 29 electrons, well, the first two of them went in the K shell. They were like right there. The next 8, 1, 2, 3, 4, 5, 6, 7, 8 went in L shell, and then there was 18. When all was said and done, copper had one valence electron sitting out there. So that right there is the valence electron. Well, I want to talk about a couple things about this. An atom of copper, 29 electrons. Two things I want to talk about. Number one, all those 29 electrons are moving around this nucleus at the speed of light. They're moving extremely fast. Because of that, chemists talk about an electron cloud existing around the nucleus of an atom because the electron is really everywhere at once. So you can really kind of think about an atom, even though we know they're not solid spheres, because the electrons are moving so fast, they develop this electron cloud around the copper nucleus, and we can just draw the atoms as these little negative charged spheres, like that. And what I want to do is I want to take this electron, which I want to make red. I want to take this electron and move it through the wire. I want to have electric current. If I take electrons and make them move, I got a current. Well, how to do that? How do I make this electron move? Or how do I make a group of electrons move? Well, the way you do it is you got to push it with an electromotive force. Where do I get electromotive force? I got to have a voltage, a separation of charge. So if I apply a voltage, if I make this end of the wire positive, and I make this end of the wire negative by putting a battery across the wire, then what I have is I have an electric field that will move through the wire, like this. And by the way, the electric field actually moves at the speed of light too. The electric field is going to move through the wire. So I can think about it like that. Well, once that electron feels the force, remember, fields carry forces, fields carry energy. So now I can feel the force of repulsion from this negative charge. At the same time, the force of attraction from the positive charge. This thing's going to take off moving that way. But as it's moving through the wire, now look at that wire. Think about it. It's not like a pipe. A pipe doesn't have anything in it. Water can flow through it. As that electron moves through the the wire has actually got things in the way. It's got these copper atoms in the way. So this is actually going to collide with that copper atom and just kind of bounce around in here like a billiard ball. You ever play billiards and see the ball bounce around the table? Every time it bounces, it gives up a little bit of energy. And so this doesn't have a straight shot through the pipe. It's going to bounce around, hitting these atoms, and every time it collides with the atom, it's going to give up a little bit of energy in the form of heat. Just a little bit in the form of heat. But eventually, it bounces around and it makes its way out. That's one charge. This electron is going to have less energy here than it had over there, because in all those collisions, it's giving up energy, just like the ball going down the hallway, but it's giving up energy in the form of heat. So the wire's a little warmer, the electron's a little less energetic when I get it down there, but it made it through the wire. Well, remember what I said. We don't move one electron. We package electrons in coulombs, trillions and trillions of electrons. So I got many, many electrons experiencing the same thing where it's colliding. I call it the billiard ball effect. It's colliding and bouncing around. If you take the sum total of all those collisions, that's what we mean by opposition to current, flow, or resistance. The fact that it's not a pipe, it's a wire. It's not a straight shot through. It's these collisions, and the more collisions it makes, the higher the resistance. So that's going to be determined by the material. A really dense material with a lot of atoms packed, the resistance of that material can be higher than if I had materials that are less packed, less atoms to run into. So the actual, on an atomic level, one way to think of resistance is these collisions with all the atomic or subatomic particles that make up that material. The important thing, though, the takeaway is electrons, and when I have resistance, or I should say current resistance, is always going to be a byproduct of heat. And that comes from resistance. Okay, so I can sum it up real fast. I mean, we took a long time to get to this point. And I can say it real fast in just seconds, but it took a lot to get to understanding. We know that voltage is a separate charge. We know that current is charge in motion. We know there's a cause and effect between voltage and current. Voltage is the cause, current is the effect. It takes a voltage to cause a current. It takes a voltage or potential difference to get electrons moving to create the thing that you call current. Once those electrons are moving, if it's moving through a medium such as a wire, copper wire, or some other medium, it's going to collide with atoms in that medium, and it's going to give up energy in the form of heat, and that collision creates an opposition we call resistance. So voltage, separation of charge, current, charge in motion, resistance, opposite of current flow. And so there it is. I want to do one more thing, and we got time to keep going to get into module 2 material, but I don't think I want to. I think we're going to end up with a short video today, but that's okay. Let me show you one more thing, and I think that's going to be it for today. Unless you have questions, I'll be happy to answer any questions. We're going to do a lot with this idea of voltage, current, resistance. And so in electrical engineering, it turns out that we do a lot of what we call diagramming. You got to make a lot of pictures. And I mean, how do you, these are abstract ideas. You can't see a voltage. You can't see a current. You can't see resistance. So how do we represent abstract ideas in a concrete way? Well, it turns out that there's a diagram electrical engineers use called a schematic. I don't know how this, let me see if I, schematic. I think I spelled that right, but it's schematic. So this is just an electrical diagram. if you were going to design something, electrical device, the way you would show it to another engineer is by the schematic or the electrical diagram. You'll start to use schematics in labs because you can also use schematic to see how to hook something up. So when you do your lab, you're reading a schematic. So you got to get good at looking at schematics. Well, on a schematic, you got to have a way of representing voltage, current, and resistance. So what I want to do is show you how you would do that. So anytime I have a separation of charge or voltage, there's three symbols, graphical symbols I can use to represent voltage. So let me show this a different way. So for voltage, I can use this symbol. I can use this symbol. Or I can use this symbol. Let me talk about all three. First, notice that on the first two, the top line is longer than the bottom line, and that's done on purpose. The long part of this represents the positive terminal, and the short line represents the negative terminal. So right there, long line is positive, bottom line is negative, over here the same way. And this one's already marked as part of the symbol. So if I had a car battery, I might say, all right, I got 12 volts. So I might show it like that. 12 volts minus like that. You would draw it like that. Now, the first two, there's actually a difference between the first two. This first one is a battery. And this is a cell. You should understand the difference between batteries and cells. A cell is just a single voltage producing unit. The word battery means group. So you have a battery of cells, or people just say, they drop it and call it a battery. But a battery is a group of cells. And so often people use the term cell and battery, they use it the wrong way. A cell is an individual voltage producing. I'm looking around to see if I have one. Let me see if I have one over here. I don't have one. But like if you go get a double A, you go to the store, you buy a double A battery. That's really not a double A battery. That's a double A cell. That thing is just one single unit that produces voltage. It doesn't become a battery until you take more of them. Let's say you take 2 or 3 of those cells and you put them in the back of it. You unscrew the back of a flashlight, and you put them in the end like that. Now you have a battery of cells. You have a group of cells. So you just call it a battery of cells, or a battery for short. And then the symbol, the battery shows 2 of these together to show it's a group of cells. So strictly speaking, a cell is an individual thing that you can hold in your hand that produces voltage, like a double A cell or a triple A cell. The square ones, which are the transistor batteries, are 9 volts. It's really a cell, transistor cell. It doesn't become a battery until you put groups of them together. So strictly speaking, there's a difference in a battery and a cell, but for the purposes of this class, you can use them as if they were the same. I don't care. The other thing you'll notice is that sometimes when you deal with a battery, sometimes I might have V, and again, if it's a car battery, I might see it like that. That stands for voltage, that's positive, that's negative. So I got a 12 volt battery, but sometimes you'll see it like this. So if you ever open up an electrical book and instead of using the V, it's an E, it's the same thing. You know, that's plus and minus. Instead of using the V for voltage, they're using the E. Remember what E stands for? It stands for EMF. Electromotive force that we talked about. They're so closely related, some people can consider an EMF a voltage. Strictly speaking, they're different. A voltage is a separation of charge. The EMF is the force applied on a charge that's free to move when you put it into the electric field caused by that voltage. but they're so closely related that some people just use the EF and V. They can use them interchangeably. So you can have E or V there to label it. And of course, this is just a general type of voltage source. It's not a cell or a battery. It's just a general representation of a voltage source. So I can represent the voltage by drawing one of these symbols. Current, let's talk about current. The way to represent current is pretty easy. It's just an arrow. So current is just an arrow, and usually put an I there for current. So if I have 10 coulombs per second or 10, I might show it like this. Now, the direction of that current turns out to, the direction of this arrow turns out to be kind of important. I'll tell you about that in just a second. Let me do resistance. Now, we're going to actually spend some time because your first couple labs deals with resistance. I want to go into some detail. I got to wait till everybody get their parts. I'm hoping that if you didn't get your part kit on Saturday, I think I have 4 students come up and get their part kits on Saturday, 4 of my students. You want to come up there and get them. Today, again, from 3 to 6, you can get those parts. Because when we hit the ground running with the lab, the actual hookup part, you want to have all the parts there. But anyway, I want to spend some time talking about resistors because they're very important, and I got a lot to say about them. But to represent a resistance, we're going to use this symbol. It's like the bottom of a saw. And it doesn't matter if it's horizontal or vertical. Okay, so I can actually show a circuit by putting these symbols together. So let me show you how that looks. And this will be a very simple example of a schematic. I might have a voltage source and a resistor. That's positive and that's negative. The long line is positive, the short line is negative. And this, I label that V for voltage, and I label this R for resistance. Now, I don't think I mentioned the unit for resistance. The resistance unit is the ohm, ohms of opposition. And they show it like this. So if I have a 15 ohm resistor, I can go 15 ohms, or I can say 15 and I'll show it like that. That's the Greek letter omega, or ohms. So this is a circuit. This is what I mean by circuit. So I should be able to draw that circuit when you guys get good, at reading schematics. This is a really simple circuit. All I have is some kind of device that has resistance. I got a power source that happens to be a battery, and I show them connected up. These lines represent wires. And so current is going to flow. And if I want to show the current flow, I would do this. So that is a complete schematic showing my power source, showing my resistor or load. That's called the load. The load is the thing that's absorbing the power. This is giving power. This thing is absorbing power. Even though I'm showing it as a resistor or resistance, it could be a light bulb, it could be your cell phone, it could be whatever's taking in the power. We just represent it as a resistance. Let me talk one more thing. Now, from the discussion that we had today, notice the way I have current flowing. I have current going this way in the circuit. And we just had a discussion today that if I take an electrical potential difference, so I got minus charge here, I got plus charge here. Then there's going to be electric field. Electric fields always go from plus to minus, so the electric field is like this. That's the E field. And if I have charge that's free to move, current, if I put that here, it's going to move that way. Like charges repel, unlike charges attract. That's pushing this, that's pulling that at the same time. The pushing and pulling forces are going through the electric field. This charge is going to move that way. So you can see that charge actually moves from the negative polarity to a positive polarity. But that's not how I have it drawn here. Current actually does this. It goes from the negative polarity to the positive polarity. That's the correct way to draw current. When you draw it that way, it's called electron flow. When you use electron flow on an electrical diagram, what you're showing is the actual path the electrons take as they move in the circuit. So in reality, electrons are going this way. Well, then you might think to yourself, if they're going this way, why in the heck are you showing it the other way? Well, when I show it the other way, that's actually called conventional current. So this is conventional current, that's electron flow, and which one you use doesn't really matter. If you want the actual flow of electrons, some books will use electron flow. If I don't have your book in front of me, if you have your textbook and you look at the front cover of your textbook, it'll say whatever electronics, but it'll say conventional current version. You can get the same book in electron flow version, and if you get the electron flow version, the two books are exactly alike. It's just all the currents in the book are drawn the correct way. If you get the conventional current book, which is what we have, we draw it the other way. And you might say, all right, well, why are we doing that? Well, the reason we're doing that, some people like to work with conventional current, which is a made-up current. It's just the reverse of electron flow. See this low potential here? Think of water flowing. Water flows from a high level to a low level. So I'm thinking of water flowing in a pipe. So what about a pipe like this? And it went down like this. And I have water flowing in the pipe. The way the water is going to flow in the pipe, the reason it's going to flow is because there's a potential difference. There's a potential between here and here. So the water flowing in the pipe is really water just falling that's been pulled down by gravity. This is at a higher potential than that, so I can mark that positive and this negative. So in nature, things flow from a high potential to a low potential. Whereas you look at this, it looks like it's doing it the other way. It looks like current is going from a negative to a positive. It is. It's moving from negative to positive because of the way we name the electron and the proton. We call the proton positive and the electron negative, so it makes it look like that I'm going from a low potential to a high potential. If we call the electron positive and the proton negative, then we wouldn't have to worry about that little fact. It looks confusing. So what they did as kind of a patch, just you know what? Even though we don't think of water going uphill, so that's an impossible situation. It's just we named these the wrong way. I'm going to make up this other current. We'll just reverse the electron current and call it conventional current flow. I like and use conventional current flow, so it doesn't matter what you use as long as you're consistent. If you use conventional current flow, use it throughout all your diagrams and calculations. I'm going to, and your book uses conventional current flow. Some books use electron flow, so I was going to say if you want to use electron flow, it's up to you. But I'm using this. All I'm asking is that you be consistent with whatever you're doing. So we did a lot today, and there's more to do. The next thing I want to do, which we'll start, I won't do it today, but we know we looked at these big three. I call them the big three. We looked at voltage. We looked at current. We looked at resistance. Those are our big three electrical terms. In the next class, what I want to do is how are these related to each other? We know the voltage is the cause. We know the voltage is the cause of current. It takes a voltage to make a current. And one side effect of having a current is that I'm going to have resistance, which is going to cause heat. But how are these related to each other? So I want to talk about relationship between these, which is going to be the most important thing we talk about, a very fundamental relationship. And then I'm going to introduce two other electrical terms. One is called power, and the other one we already talked about today, but not connected with electrical quantities, and that's energy. So I want to know the relationship between these. About that, and then we'll learn about what is power, what is energy, and how are they related to the other ones here. Turns out that we can measure, and we can measure these directly. We don't have the ability to measure these directly. I mean, there's equipment that will do it, but we don't have the ability to do it. But given these, we can always calculate these. So we're gonna bring this, what, 5 of these. We'll bring it all together, and your understanding, and hopefully you'll see how everything relates to everything else. So guys, that's enough for today. I think you listened to me talk long enough. I want to dismiss. Before we do that, I need to take attendance. Remember the 2-week thing? So week 1, if you sent me a text with your name in it, I got you down. We got to do that for 2 weeks. Actually, I'm going to continue doing it, because not only do I have to know that you were there, if you end up dropping the course, I got to be able to say when you dropped the course. So we're going to take attendance. Before I do that, does anyone have any questions before I erase this on either this or anything we talked about so far in the class? Any questions? Okay, well, then what I'm going to do is I'm going to put the information here. I want you to text me. This time I don't need your student ID number. I just need your name, first and last. So text me your name, first and last, and make sure you put EET 131. That's important because I got a lot of other classes texting me. So send me that. You want to text it to 513-494-6162. If I don't get a text from you at that number, like right now, I'm going to assume that you were not present in class. So I saw a couple people leave the session. That's not good. You want to make sure you send me this. Go ahead and send it now. And then the only other thing I want to say is, please, if you have time, go over to campus today between 3 and 6 and pick up your kit for your lab. It's just one small kit. I can also, I'll be over there probably a little after 4, but there'll be somebody there at 3 if you want to come early, and I can show you the trainer, the actual trainer. So I know someone had a question about it. If you come up there today, I'll probably be there around 4:30, but there'll be a gentleman there at 3, from 3 to 6. But I got a class that I'll probably end around 4, so I'll get over there a little after 4. I can actually show you the trainer if you want to see it. But I will put the link out there for the trainer and for the digital multimeter. All right, guys, that's it. Thank you, and I will see you later.
Hello, Professor.
Yes.
Professor, last time you told me you will send me a link to buy the